Right. So, very good day to all the ladies and gentlemen. Now, what about today? Today's concept. No, no, not today. This moment's concept. The new one that we will learn is nothing but regarding the PV plot. The PV plot, and here we'll be discussing two of the important points. Number one is that if this is the pressure and this is the volume over here, and there's nothing but some cyclic process over here, in the area under this pressure versus volume is nothing but given as the work done by the gas itself. It is given as integral of PdV, and if it is cyclic, just put a cyclic integral over here, and we'll call this as the cyclic work or work done per cycle, right? That is nothing but this particular area which is encompassed within this particular curve, right? For example, if there is a triangle, you can do half base and multiply with the height itself, right? Half base into height, that gives us the value of the cyclic work. Now if the arrows are such that they are nothing but in the anti-clockwise sense, in that case the work is nothing but a negative value for one particular cycle, right? Another concept let us explore. The second one itself is that you can find out the molar specific heat from the PV plot. Molar specific heat from whose plot? Not your plot, definitely from the PV plot. Now for that, how do you define the molar specific heat? Over here there is some gas which is present, let us say enclosed by a piston arrangement over here. You supply this one a certain amount of heat, it does a certain amount of work, and there is a change in the internal energy of delta U. From the first law, we just write it as W plus delta U. The Q value, you can always write it as number of moles into the molar specific heat multiplied by delta T. On this side, this is nothing but the work done, which you can find from the PV plot. Plus delta U is nothing but NCV multiplied by delta T. The CV values are for monoatomic. This you have to remember. The CV is nothing but F by 2 multiplied by R, where degrees of freedom are 3. So you get 3 by 2R. That's your CV value. Remember this one. For diatomic, without considering any vibrational degrees of freedom, the CV is nothing but 5 by 2 times of R. And then you have the polyatomic also, where we consider the vibrational degrees of freedom also. So therefore over here you can always write the C value as equal to W divided by N delta T plus the CV value itself. For example, let us consider over here a process which is in this way, let us say, right? The process called this is the state over here, which is A. This is the state over here, this is the B. And let's say that this is your volume, which is nothing but, let's call this as V0 over here, and let's call this one as 2V0 over here, and let's call this one as how much? Let's call it P0 over here. And therefore this one over here, it must be equal to 2 times of whom? Because since it is extrapolated masses through the origin, therefore that must be 2P0. So now we want to determine what is the value of the molar specific heat for this particular process over here. And the gas over here is nothing but, let us say, monoatomic, and the number of moles over here are nothing but, let's say, N number of moles, right? N number of moles are there. Initial temperature is T0. That means T0 is nothing but the temperature at A, let us say. Very standard problem. So all we need is to find out what is the area over here under this AB line and the volume axis. That will give us the work. We'll simply divide it by n delta T and find out what is the molar specific heat. That's all. So for this process, we'll just divide this into two parts, and we can write over here that the W is nothing but equal to how much? The triangle area plus the rectangle area, half base into height plus V0. That is nothing but your W. Now coming to the C value is W by n delta T plus the CV value. For monoatomic we know F by 2R, 3 by 2R. And over here we'll substitute the value of W as equal to how much? This one is 3 by 2 P0 we know. Divided by N. Delta T is the temperature at the B point minus the temperature at the A point. Therefore we can write, for the temperature at the A point, this is already known to us. It is the T0 value itself. We need the temperature at the B point. For this one, let's use the ideal gas equation. Pressure at A, volume at A is nR into TA, or you can write PAVA by TA is PB VB by TB. Let's substitute the values P0 V0 by T0. There what do you have? 2 times 2 times 4 times by TB. Therefore you can write the TB value as 4 times of T0. Let's substitute this one over here in the place of this TB. You get 3 by 2N P0 V0 divided by 4 T0 minus T0 plus 3 by 2 into R. And now we just have to replace this P0 V0 over here. Also, using again the same ideal gas equation, P0 V0 is nothing but nR T0 at the A point we have used. So you can write this as nR T0 divided by 3 T0 plus 3 by 2 times of R. That's it. This you can cancel. This also you can cancel. What else you can cancel? R by 2 plus 3 by 2. You get this as 4 by 2, which means it is 2R. That is your solution right there. This part is clear, gentlemen, no doubts. Yes. Molar specific heat